give me a moment. There's some student wanting to come into the class.
Eugene.
Yes.
Oh, that might have been what you just said, but someone was added to the class. There was a request for them to join the teams. Can you accept that so they can join the Microsoft team?
I'm doing that now. Thank you.
Okay.
Okay. Right. Okay. So now, that is what. So this is what we mean by the range of deformation speed. Okay. When it's 0, you get a very wide range. When it is higher in value, the range are very small. Okay. So now I'm going to compile. I'm going to write down all the material behavior, okay, into a table, which you'll have. Okay. I'm going to put all into a table now. Okay. Any questions so far from anyone, please?
So this range, 200 to 300 for AISI, and then all the other alloys. Can we just so was that derived from the equation here?
No, these are determined experimentally.
Oh, okay. Okay.
What are the units for strain rate?
So strain. Hold on. So strain epsilon dot or epsilon is equal to change in L divided by L naught. So it's unitless, yes or no?
Yes.
So strain rate is basically 1 over a second. That's it. Does that make sense?
Yeah, I didn't know if that was like inch per second or something.
No, it's just strain in the rate of deformation. Okay. Right. So I'm going to put onto a table. Okay. And this table is important. Okay. I'm not going to erase this table at all. So we have looked at 4 materials now. Okay. Yep, you can see that. So we have AISI 1045. You have foosball. We have dual phase steel. And we have trick. I'm just going to write down the mechanical properties, okay? Next week we'll deal with the chemical composition, okay? Then we have the A value. Then we have the B value. Then we have the N. C. And M. Okay. So I'm going to write all. So this is 5.1. This is 600.8. This is 0.234. 0.022. So when you're in a manufacturing world or design world, you'll see all these values. Okay, you see if not, you have to determine these values. Later on, I'll teach you how to determine them. Okay, so you got 4630, right? And then you got 0.253. We know why C is equal to 0 over here because we cannot find the value, and this is 0.1245. Okay. Then we have dual phase. We have 120, 1020. Okay. Then we have 0.196. Then we have 0.125, okay, 0.196 and 0.125. And then you got 1.287. Then you got M value. Then your trick, we have 412, followed by 2153, right? 0.66. And then you have 0.014. And then you have 0.76. Okay, 0.76. So the thing to take note now, okay, once you have all these value, okay, you look at very distinct magnitude, okay, like you'll see this, whoa, look at this, so high, right? This is like so high. Then you have for B, this is also a high value. Whoa, what's going on here, right? Then your N, you see this trip still, right? The N is also like 0.66, right? It's about 3 times higher, okay, 3 times or 2.5 times higher than USB or ARSI 1045. Then you look at the C value, right? So now I point to you the C value is 0.125. You have a feel, right? Whoa, right? If you look at dual phase steel, this is 0.125. Nickel base is only what? 0.05. Look at that, 0.125. You're like, yeah, this is a bit scary, isn't it? Okay. And then you have an M of 1.287. Okay. Then you also look at over here, we have a M, okay, that is also very low down here. Okay. Now, okay, there is some more people trying to get in. I still do apologize. Let me see. Okay, right. So now let's put ourselves into the manufacturing engineer. So we're going to write things out by looking at this table. Let's consider we are looking at manufacturing process planning. Okay, by looking at these numbers. Okay, so if we look at USB 1500, right? You look at, so when we look at USB 1500, we know like this is really difficult to deform, right? It has a very high yield strength. Not only high yield strength, it was strain hardened very quickly, right? And in order to deform this material, we have to make use of what? Heat. Because M is equal to what? 0.1245. So you know by looking at the mechanical behavior, right, what all these numbers means, you immediately can write down external, okay, for AIR, for USB, we need what? External heat source, right? We need external heat source should be used right? Should be used to reduce the strain hardening effect. Okay, so strain hardening effect is the high A, B, and N, or B is the one that is the vicious one. Okay, then you start looking at dual phase steel. You start doing, and dual phase steel, you have C equal to 0.125. So what does that actually mean for a manufacturing engineer? Okay, what does it actually mean for a manufacturing engineer? If C is equal to 0.12 or 0.125. So I'm going to write down dual phase steel. So what it means is do not use high strain rate to deform the material. Okay, do not use high strain rate to deform the material. This is because C is equal to what? 0.125. Right? 0.125. So when demand increases, okay, we spoke briefly about this. We outsource. So outsource over here means you hire another company to help you produce the part, and okay, outsource first, followed by purchase of more machine tool. Okay, so this is more of a capital investment. Okay, so depending on how on is the business here to stay? If the business is here to stay, you have to buy more machine too. If not, you just outsource. Okay, and then if you look at dual phase steel, the N is so high. Unfortunately, it needs a lot of heat, energy. Okay, if you're going to use heat to soften the material, soften the material at high strain. Okay. And then finally, you look at strip steel. Let me underline this for you. Okay. Then we look at strip steel. Okay, we look at strip steel. So again, N is very high. So what it means, you have to control the plastic strain. Okay, you have to control the plastic strain during deformation. Yes.
Sure. Quick question.
Yes.
I'm kind of confused. So when you're saying you need to heat it up, so what are we trying to reduce by heating it up? We're trying to
you're going to reduce the flow stress at large strain.
So like in application, like let's say you're machining. So is this, so you're saying heat up the material before you start machining, or what?
Okay, so for this, okay, it's not just for machining. Okay.
Oh.
It's not just for, it can be for bending.
Okay.
It can be for machining. Okay. So
Okay.
anything that has deformation, because whether you machine or you produce material, you still have to use a standard stress strain curve. Am I right?
Mm-hmm.
Okay. So for this material, okay, if you're going to deform it, okay, at high speed, you need your heat. But you need a lot of heat.
Okay.
Okay. Whereas if you compare to standard 1045, you don't need to put so much heat, because if you increase the speed, the flow stress will not increase very significantly.
So would there ever be a scenario where you would have to cool the material before doing something to it?
How do you mean? How do you mean you have to cool the material?
You know how you're saying heat up the material, so then you get like less flow stresses, right?
Yes.
Yeah.
So whatever you heat up, you have to bring it back to room temperature. That's for sure.
Okay. So like I've come across some tooling before. It's like super cooled tooling for machining. So doesn't that cool the material while it's machining? So isn't
No.
it like, no?
Internal heat, okay, for that ductile material, the internal heat energy that is generated, whatever tool you use, will